energy in a wave. So energy transported in a wave. So as energy propagate in space, the wave carry energy. So when the wave is moving, it has energy in there. So how do we calculate this energy? Or how do we think about this energy? So energy, it's denoted as E. In SHM, so simple harmonic motion, we have the energy is equal to 1/2 K, the spring constant, and A is the amplitude. And amplitude in a periodic motion is equal to the maximum X, which is displacement. So we're going to carry this periodic motions. One of the examples is SHM, and how they come up with the energy. We're going to use that, apply that into what are we considering here. So in general, is the wave. But in SHM, we have periodic motion. A periodic motion, it's a wave behavior. So then you can say energy, it's this equal to 1/2 Ka squared can be also treated in the, can be also used in the waves consideration for energy. So energy for wave in general, it's proportional to amplitude squared. So amplitude squared here. So I know this is not like perfect mathematical proof, but you get an idea of, since this is from periodic motion, and periodic motion behave like a wave, right? So if you draw X versus T for this SHM, it is a wave, right? So then we can say, well, for the wave, it will have this proportionality, right? Which is E is proportional to A squared. So now intensity is defined as power divided by area. And power P, which is capital P. And we are not going to use A because A is being used for the amplitude. So we're going to just say area here. So power is energy divided by time, or energy consumed in the time interval. So then based on that, you plug this E divided by time into here. So then intensity I is equal to energy divided by area, and then also divided by time. So there's a modification there. So now based on that, so you have I is this, but if we say area and time is constant, right? Whenever the area is constant and time is constant, then your intensity must be proportional to the A squared too, because I is E, just divided by area and time. So I and E behavior is similar. So then you can say, since E is proportional to A squared, so then I must be also proportional to A squared if this part is constant, because I is E divided by that, and that's constant. So then I behavior and E's behavior to the A, which is the amplitude, is the same. So they are similar. So now if we say P is constant, which usually is the case. So if you have a light source and the light source power is usually constant. So how much time you consume, how much energy, all the watts, right? So this is in the unit of watts. Right. If P is constant, which basically says that in a certain time you will send out how much energy, that's constant, then I is proportional to 1 over R squared because area, right? Because of area. Because I is proportional to 1 over area. But area is proportional to 1 over, proportional to R squared, right? So area is proportional to r squared. So then I is proportional to area. So then so then this one here then says I is proportional to area, which that is proportional to r squared 1. Right? So then that's what we have. So intensity will become smaller and smaller, right, as you move from this area, this r, to this r here. Because your source is the same, but I is equal to power divided by area. So your area is growing. So this is the area here is equal to 4 pi r1 squared. And that's 4 pi r2 squared. So you know, since area is getting bigger, if p is the same, then I must be shrinking. So then that's what you have here. All right. So then if you look at this two, this one and this one, see, I proportional to a squared and I is proportional to 1 over r squared. So then if you look at a and the r relationship, a must be proportional to 1 over r. So as this distance is increasing or the radius is increasing, your amplitude is becomes smaller. So the area here, not the area, the amplitude here and the amplitude there, right? So this amplitude is bigger. So basically A1, R1 is equal to A2, R2, right? Or you can say A2 divided by A1 is equal to R1 divided by R2, okay? So the bigger the area, the bigger the, what am I saying? Sorry. This is the amplitude. The bigger the amplitude, the bigger the radius, the bigger the radius like R2, the smaller the amplitude. So R2 is bigger, so A2 is smaller. So R1 is smaller, so then A1. A1 is not area, it's the amplitude. Okay, so we're going to stop there. So what we're talking about is what is the energy inside the wave. So as the energy is moving, right, it carries the wave. I mean, as wave is moving, it carries the energy. And so in this discussion, we find out a lot of proportionality, right? A lot of proportional relationship, or in this case, I and R, it's an inverse proportional relationship and has a square, right? So so this, you say the I is inversely proportional to 1 over, no, it's inversely proportional to R squared, right? So that's how you say it. I is inversely proportional to r squared. Or you can say I is proportional to 1 over r squared. Okay? All right, so that's the energy in the wave. Okay? Bye-bye now.